let's go for this example. I want to apply that strategy for solving that, for that thing here. So what am I going to do here? So the first thing I'm going to do is I'm going to bring my strategies up here. And what I want to do here is that I don't want to tell you how to think, because I think you gain a lot by you doing it your way. You're not supposed to do it Carlos's way. I'm supposed to give you suggestions of organization. You have to organize you. These are suggestions, but I promise you one thing, you have to go through these steps in some shape or form. Okay? You have to go through this process in some shape or form. So here we go. So what I want to do here is that I want to draw a detailed motion diagram of this thing. Okay? So I'm going to read this problem, and then I'm going to go right through the steps. So I'm going to say step 1. Here, I'm going to draw a motion diagram and plot velocity versus time. Why am I doing that? The whole goal is to identify intervals of acceleration. And you want to be careful when I say motion diagrams. I am not talking about detailed motion diagrams, okay? I am not talking about detailed motion diagrams. What you're going to see here is that what I'm really after is essentially going after situations where I know what the velocities are, what the accelerations are at the interval points. Here I go. So let's go read it. So the first thing I'm seeing here is that I'm seeing this. It says, Alfredo is driving his car when he suddenly sees a box out in the middle of the street. In a long blink of the eye, 0.4 seconds, Alfredo reacts and changes his velocity from 85 kilometers per hour to 45 kilometers per hour over a distance of 105 meters here. So look what it says here. He reacts. That means he's on the accelerator, and then he has to take his foot off the accelerator and onto the brake. So that means when he takes his foot off the accelerator, he is moving at constant velocity. It's not until he starts braking that you have deceleration. So I'm going to set it up here. So what do I know here? So I'm going to set up my intervals. So my first interval, and look how I'm setting up my thing here. My first interval says that he's driving at some initial speed.
Hey, Carlos.
Yes.
So we're assuming that like the system in this equation, in this example, is frictionless, right?
No. The fact that there's braking means that there's friction.
Okay, so wouldn't it be then that as soon as he took his foot off of the accelerator, he would start slowing down incrementally?
Oh man, you're one of those realist people that really see all those details. Man, unfortunately, you are absolutely correct that you would assume that if you took your foot off the accelerator, that you should be slowing. You are absolutely right. Unfortunately, this is a book problem.
Okay.
And in book problems, when we say reaction, reaction means, like you said very clearly, you have, you assume frictionless. But then all of a sudden, as soon as you hit the brake, now there's friction.
Right, gotcha. Just friction in a different part of the system. So like within the vehicle as opposed to between the vehicle and the street.
Yeah, no, you're absolutely right. Yeah, very clever observation. Thank you for that statement. So moving on here. So I know for a fact that he's moving. So when I'm looking at this thing here, note that this region, you know what? I need to move this down a little bit just so that, because I want to talk about that this is the reaction part. And this reaction, I'm going to call this my interval 1. So he's moving at this constant acceleration, and we say, at this 0 acceleration, and by the way, that's my motion diagram right there. I'm not drawing all this other stuff. We're done with that. So if I'm moving with constant velocity, look how far I've gone now. My velocity right here goes to right there, right? So this is my reaction time. And now I start a second process, which is the braking time. So now I'm in the braking interval. And what am I going to call this? Interval number 2. So what you're seeing here when I'm drawing this thing, look what you're actually seeing here. Look how, if I know the velocity initially, I know what the initial velocity is at interval number 2. And as soon as I do this here, what's happening? I now have a braking process. That means I have an acceleration that's negative because it's pointing in that direction. Okay, so I'm braking. Now, if I continue to read this thing here, it says I go from 85 kilometers to 45 kilometers. So I'm going to brake over some distance here, and I'm going to say that it doesn't say that I'm coming to a stop, but I do know that when I get to this point right here, I now have a slower speed. Right? So in other words, if I look at this distance here, this is my distance from here to here, which I don't know anything about because they don't tell us what that distance is. This is my second distance. This is my braking distance. But what I do know from the question here is it says that the braking going from 85 to 45 is 105 meters, right? 105. So in other words, when I look at my distance from here to here, I know that my total distance is 105 meters from there to there. So as of right now, that is my motion diagram for this problem. So a couple of things that I would do here is that then I'm going to go to step 2 here. So I think I've identified everything, right? I've identified everything. So now let's look at some details here. If I go to step 2, what am I doing? I'm going to say then, because it's moving to the right, guess what? This is positive. This is negative. So now I define coordinate system.
Hey, Carlos.
Yeah?
For the braking in the interval 2, it's not necessary for you to show the actual braking with the velocity, like going lower and lower and lower to actually demonstrate.
No, dude, that's chapter 1.
Okay.
I think we've already done that. And so you know that if I have deceleration, I should be drawing vectors that get smaller and smaller. By the
Right,
way,
but for the motion diagram, like it wouldn't be necessary for us to show that velocity vector get like decreasing and going beneath, like below. That's not necessary.
I don't think so.
Okay.
I think this is clean enough for problem solving.
Okay.
But we know for a fact that it should be getting smaller. So then I'm going to go to step 3 here. So step 3 says I'm going to convert all units and set up a data table. So the first thing that I see here is that V1, they tell us, is 85 kilometers per hour. V2 is 45 kilometers per hour. And I see I missed the 5 over here. So let me put the 5 back. So if I go in and I do the calculation, assuming that I did the right numbers, I convert this and it becomes 23.6 meters per second. And then this guy is 12.5 meters per second. Now note, this is 3 significant figures, but in the end, I'm going to reduce my calculation all the way down to 2 sig figs. But for right now, that's what it is here. Now I want to make sure that I get all of the information on my table here, because I haven't really finished reading the problem here. So look at that. He's driving, he suddenly sees the box in the middle of the street. In a long blink of the eye, he reacts. So note, there's another piece of information that's here. What's this other piece of information? You're seeing that from here to here, the time of the first interval is 0.4 seconds here. Do I know anything about the braking time? The answer is no. There's nothing about the braking time. So it turns out that my braking time from here to here is not known. So note, in interval 1, what is it that I don't know? I don't know the distance, and that's it. When I look at braking interval, I don't know the acceleration, I don't know the distance, and I don't know the time. So there seems like there's a whole bunch of unknowns that I don't know. So here I go. So let's set up the table.
By the way the question is worded, like it does seem a little bit like not very plausible, but the way it's worded almost makes it sound like their reaction time and the braking like is in that 0.4 seconds.
Yeah,
It doesn't seem
yeah. The reason why I say that it doesn't, because it says this here, right? It says, in a blink of a long eye, he reacts.
Okay.
And I'm reading that as one phrase.
Okay.
Now, it could be, Linnea, that I have 45 years of reading problems, and so I'm so goddamn practiced that it may look like I know what the hell I'm doing some of the times. I'm not really sure if that's true, but it's just that I do think that that's what it's saying.
I mean, yeah, like that makes the most sense to me, because otherwise that'd be kind of like crazy. But the way it's phrased, like, makes it.
Yeah, I can totally see what you're saying.
Okay.
So now let's look at this thing. There are 2 intervals. There are 2 intervals, and we need 2 data tables. Right, this is just for organization. So here I go. So what I typically do here is that I come in and I label them like this first.
Aren't there technically 3 intervals?
Not for the first question, right?
Ah, gotcha.
You're right though, and C, there's going to be 1.
Yeah, that's what I was looking
But
at.
I'm just really just going off of this picture here. So look what I do here. So what I'm going to do here is I'm going to say, look, I'm talking about interval 1. So what do I know about interval 1? Well, I'm talking about distance x1. I'm talking about acceleration 1. I'm talking about time 1. And right away, I don't know what the distance x1 is. Do I know what the initial velocity is? Well, yeah, this is typically the final velocity, and this is the initial velocity. The fact that this guy is 0 tells me that those 2 velocities must be the same and must be 23.6 meters per second. And then if you look at this thing here, note that the time interval during this thing is what? 0.4 seconds. Do I know what the distance is? No, that's an unknown. So now what I'm going to do here is that I'm going to go in and look at the second interval. So when I look at the second interval, I know this is 2, this is A2, and then I'm going to have two different velocities now. So what do I know about interval 2? Well, do I know what the initial velocity is? Yeah, because we see that the initial velocity in the reaction region is the same as the initial velocity in the braking region. So I could immediately come in here and say, I know that V1 is what? It's going to be 23.6 meters per second. That's really small. You know what I'm gonna do? I'm gonna make this table a little bit bigger. I need more space. So this should be 23.6 meters per second. And when I look at my picture, do I know anything about the final velocity? Yes. We know that that speed from what we just talked about is 12.5 meters per second. Do we know anything about the time? No. Do we know anything about the distance? No. Do we know anything about the acceleration? I don't think they told us about the acceleration. So what you're seeing here is that there's a lot of things I don't know in the second interval.
Carlos,
Yes.
since we know that we're gonna get delta x1, would we just say that it's the 105 minus delta x1?
That's exactly right. That we can get this distance here. So then you got to go back and you got to look at your problem. So what we do here is that from interval 1, we can get this guy right here, right? So in this case, if I do this thing here, I could see here that I'm going to get what? That I can get that x total is the same as delta x1 plus delta x2. So getting delta x1 tells us what delta x2 is. And then I got to look at what the question says. But you could see here is that this is really what we don't know, T2 and A2 for that interval. So now I'm going to go back up here and I'm going to then read the question now. I've set up the problem here and it says, B, what is the acceleration for this interval here? So look what the question is saying. What is this? Look at this interval. What is the thing that we're missing that is not given in this problem? It is time. The thing we do not have determines the equation to use. So let's go do this then. So in order to calculate this acceleration, I got to get delta x2. But as Ilian said, if I know the total distance, then I could get x2 here. So what I'm going to do here is that the first thing I need to do here is that we first need to determine delta x1. So let's go look at that. So the thing that I want you to think about here is that I have my kinematics table.
Hey, Carlos, what's the difference between the question marks and the X's? Like why, like how? See, I would say that we don't have the acceleration.
But that, no. But look what the question's asking. The question is asking, what is the acceleration? We're trying to solve for that. So the thing that we're solving for is what we put a question mark on. The variable that we do not have access to in this problem is the time. So I'm putting an X there because that's not given in the problem. So that means I either have to solve for it or I use it to determine which equation, because each equation has 4 variables, not 5.
I got it. Thank you.
So now let's look at what this says here. So if I want to calculate distance here, x1, note that for starters here, we can't use this equation. Why? There's no distance. That's why. So what about the second equation? Well, if the acceleration is 0, so if a is equal to 0, then all this tells me here is that v1 is equal to v1, which we already knew when we're moving at constant acceleration. So we can't use this equation either. So if I look at the third equation, look at what the third equation says here. If acceleration is equal to 0, then this tells me here is that delta x is equal to what? v1 t1. In other words, this is the equation that I'm going to use. So we can't use this because no delta x term. So, and if I look at this scenario here, I can use this equation, the last one, but it looks like this is the easiest one to use. So this is the equation that I'm going to use right here. So I'm going to pick that equation. So then I'm going to solve for delta x, which is v1 times t1. Then I'm going right off my table. If I go off the table, this is going to be what? It's going to be 0.4 seconds times, let me make sure I get this thing here. I'm going to get, what's my values? It's 23.6 meters per second times 0.4 seconds. And then if I go and I calculate this thing here, what you're going to find here is that I end up getting a value of 9.44 meters per delta x1. So I now know what the distance is. But remember, this immediately tells us about what? The other one. So when I look at this variable, is that this now tells us about delta x2. Because we know that delta x total is 105 meters, but we know from our picture that it's got to be the sum of these two, which then tells us that this should be 105 meters minus 23.6, which then is going to give me a distance of 95.6 meters. And that's what my distance delta x is.
Isn't the 23.6 the velocity and then the delta
Well,
x?
I'm 9.4, sorry about that.
Okay.
So I now know what that distance is, but if I now know what that distance is, I could then come up and I could take my table here. So if I go in here and I put in my second table, you could see here that I'm now going to take this value, and where am I going to pop it into? Right there. And if I pop it into here, I now have, here's my one variable. What we don't have determines equation. So what I'm going to do then is that I'm going to go get that table now. So if I get that table and I pop it in right here, look what happens. I look at my table, and what's the one variable that I don't have is time here. So it tells me I must use this equation. If I want the acceleration, I have to use this equation. There's no choice in the matter. So from the kinematics table, we have equation v squared plus 2a delta x. And so I typically don't put any subscripts on this thing because I look at my interval. Which distance am I talking about? Delta x2. Which final velocity? 2. Initial? 1. Which acceleration interval am I talking about? Is here. So you could see here is that now I've set up the equation. So now what am I going to do? I'm going to solve for A2. So if I solve for A2, look what I got to do. I'm going to bring the velocity v1 squared to the other side. So I'm going to get v squared 2 v1 squared. But note that the acceleration is multiplied by 2 times delta x2. So I got to divide that out. So then I'm going to get 2 delta x2. And here's my acceleration value right there. So now that I have my acceleration value, you know what? I'm going to run out of space. So I'm going to move this over here a little bit. So now that I have my acceleration here, what am I going to do? I'm going to plug in my values from the table. So if I look at my values from the table, what's my velocity v2? Well, it's got to be 12.5 meters per second squared. What's my initial velocity? 23.6 meters per second squared. And then I'm going to divide that by 2 times the quantity, 95.6 meters. And so if I do that, the acceleration that I end up getting at the end, I get a value of minus 2.0 meters per second squared. That's my acceleration. So my acceleration is minus 2.10 meters per second every 1 second, or I can write this as 2.10 meters per second squared. There's my acceleration. And that's how I use the kinematics table right there.